So there's a lot of rules that go into writing the ionic formulas. You've got to find all the charges. You have to make them neutral. You need to know your polyatomics. You got to use the transition metals with their Roman numerals. The covalent compounds are a piece of cake. Since the covalents are not transferring electrons, you don't have to worry about charges. There are no charges. Kind of like that. So we don't have to worry about looking things up on the periodic table and making them neutral and all that good stuff. These are going to be compounds that only contain nonmetals, which also makes this kind of a nice little task because there's a very small fraction of elements on the periodic table that are nonmetals. We're really just looking at like boron, carbon, silicon, some of the nitrogen family, oxygen family, halogens. A very small section of the periodic table. So after a while, there's not a whole lot of options here of covalent compounds I can give you to write formulas or names for. When you are writing the formulas, don't overthink this. You'll see the first name, the first element written out with a full name. The second one will end in IDE. And then you'll see prefixes that tell you how many atoms of each element are present. You'll also kind of notice, like here are those prefixes. They're the same as the hydrate prefixes. Like if we had one water molecule in hydrate, we would say monohydrate or dihydrate. Same prefixes, so it's kind of nice. So I think all of us are familiar with carbon dioxide. Carbon with 2 oxygen. Done. That's it. You don't have to look up charges. You don't balance anything. Let the name tell you the formula. This kind of tells us how we're sharing the electrons. We could share single bonds. We could share double bonds, triple bonds. And that's another thing that we'll kind of look at when we get into the bonding unit a little more. For now, let the name tell you the formula. Don't overthink them. Carbon monoxide is CO. Done. Tetraphosphorus deoxide. Tetraphosphorus P4O10. Whoa. Now, a couple things to make note of. When we write ionic formulas, we always show the simplest ratio between the two ions. We show the simplest repeating pattern in the crystal. So I would never leave an ionic formula with a ratio of 4 to 10. We would always simplify ionic compounds down to that most simple ratio. Not the case with covalents. Covalents don't exist as big crystals. They exist as singular molecules, and sometimes they're giant molecules. But we can have a molecule that may have like 60 carbons and 100 and some hydrogen or something like that. That's the true structure of the molecule. That's okay. So when we're dealing with covalent compounds, all non-metals, it's okay to have a ratio that's not simplified. P4O10 is perfectly fine. Another thing that we should make note of. Too often I will have people that overthink this and they want to get into charges. I don't know, they're just freaks about charges or something like that. And so we see carbon monoxide, CO. But they want to somehow go to the periodic table and start using charges. So they'll say, well, if carbon is the first element is supposed to be like a positive. So they'll say +4, and then oxygen is -2. So they'll tell me that carbon monoxide is CO2. I'm not lying. And right now, like at the beginning of the year when we're going through all this stuff, then they'll get it right. Oh, yeah, I remember. I look at the prefix monoxide. And then give it a month or two and they just turn into boneheads and start using charges. No, carbon dioxide is CO2. Don't overthink it. Carbon monoxide, CO. But then again, they'll say, but I can't have that. I can't deal with it. I'm going to have a breakdown. Because CO O would not be neutral because they want to freak out about the charges again. Like, but carbon is +4 and oxygen's -2, and that's not going to be neutral. I don't care. In this compound, there is no charge. We're sharing the electrons between carbon and oxygen. We're not transferring. Carbon is not losing 4 electrons. Oxygen is not gaining electrons. Not in a covalent compound where all the elements are non-metals. Don't worry about these things being neutral. Don't worry about the charge. Don't even think about charges if it's all non-metals. Writing the names should not be difficult. The first element, if you have one atom, the mono is optional. So if you have like sulfur trioxide, you don't need to say monosulfur trioxide. If you do, that's fine. Nobody will ever mark it wrong if you say monosulfur trioxide. But it's not necessary on the first element. Mono is necessary on the second element. So if you had something like SO, then I would need to say sulfur monoxide. Kind of like carbon monoxide. I have to use mono on the second element, but it's not necessary on the first. So I could say here carbon disulfide. Carbon disulfide smells like somebody threw up rotten eggs for breakfast. It smells terrible. One time I ordered it, and it came in the box. I knew right away that that box had the carbon disulfide in it. The cap wasn't on tight, so it was kind of leaking out. It smells terrible. I only need the prefix on the second. I do not need to put anything on the carbon. And the last one listed here, 2-nitrogen. Dinitrogen. And then I've got 4-oxygen. Tetraoxide. Now you could spell this a couple different ways. If you say tetraoxide, that is totally fine. If you drop the A and just go tetroxide, that's totally fine. We'll all know exactly what you mean. Here I do need the 2 prefixes, and it's okay that it's a 2-to-4 ratio. I don't have to simplify it because it's 2 nonmetals, nitrogen and oxygen, and that's the true structure of the molecule. So these covalent compounds really should be simple. Half the battle is recognizing that it is covalent, all non-metals. And then I can just write their names and formulas based on these prefixes.